Module 6. Other improvement methods. Reducing setup time is a crucial aspect of improving operational efficiency and productivity in various industries, from manufacturing to service sectors. Setup time refers to the time taken to prepare equipment, machinery, or workstations for the next task or production run. By minimizing setup time, companies can increase their output, reduce idle periods, and respond more quickly to customer demands. Reducing setup time is accomplished by converting as much of the setup process as possible from internal setup time to external setup time. Internal setup time refers to activities that must be performed while the machine or equipment is stopped, which directly affects production time. On the other hand, external setup time refers to tasks that can be carried out while the machine is running, minimizing downtime and increasing productivity. External setup time refers to the time to complete setup activity that do not require that the machine be stopped. By optimizing the setup process and shifting tasks from internal to external setup time, companies can significantly reduce the time it takes to prepare machines or equipment for the next production run. This improvement leads to increased machine utilization, shorter changeover times, and higher overall production efficiency. Another methods or improved manufacturing is a Kanban card, which is a visual signaling tool used in the Kanban system, a lean manufacturing method. It is used to indicate that the subsequent work center needs parts or materials to proceed with production. When the work center consumes parts and depletes its inventory, it sends the Kanban card back to the previous work center or materials handler as a signal to replenish the stock. This system helps in controlling inventory levels, reducing waste, and maintaining a smooth and efficient production flow. A Kanban card is a visual signaling tool used in the Kanban system, a lean manufacturing method. It is used to indicate that the subsequent work center needs parts or materials to proceed with production. When the work center consumes parts and depletes its inventory, it sends the Kanban card back to the previous work center or materials handler as a signal to replenish the stock. This system helps in controlling inventory levels, reducing waste, and maintaining a smooth and efficient production flow. Another method of continuous improvement is the Toyota Production System, TPS, and just-in-time manufacturing represents a revolutionary approach to production and operational excellence. Developed by Toyota in the 1950s, these principles have become influential paradigms in the manufacturing industry, inspiring various lean production methodologies worldwide. At the core of the Toyota Production System is the relentless pursuit of waste reduction and efficiency improvement. TPS was born out of necessity during post-war Japan when resources were scarce, and efficiency was paramount. One of its fundamental principles is muda, which means eliminating waste in all its forms. This includes overproduction, excess inventory, unnecessary transportation, waiting times, overprocessing, defects, and underutilization of employee skills. Just-in-time manufacturing, a key component of TPS, revolves around producing and delivering goods precisely when they are needed, in the right quantities and at the right time. JIT minimizes inventory levels, carrying costs, and the risk of overproduction. This approach is achieved by synchronizing production with customer demand and fostering close collaboration with suppliers to ensure the timely flow of materials. TPS and JIT place significant emphasis on employee involvement and continuous improvement. The philosophy of Kaizen encourages a culture of ongoing incremental improvements in all aspects of the production process. Employees are empowered to identify problems, suggest solutions, and participate in decision-making, making TPS not just a production system but a comprehensive management philosophy. Moreover, TPS promotes Jidoka, which means building quality into the production process. It encourages automation and intelligent machines to detect defects and stop production when abnormalities are identified, ensuring that problems are addressed at the source and preventing the shipment of defective products. Additionally, TPS and JIT prioritize Hijunka, or production leveling, to reduce the variability in production schedules. By maintaining a consistent production pace, companies can achieve a smoother workflow, reduce stress on employees, and improve overall efficiency. For example, the foundation of the Toyota Production System, TPS, and just-in-time manufacturing includes the following elements. TPS emphasizes the importance of creating simple and efficient processes that deliver high-quality products. By focusing on quality from the start, TPS aims to eliminate defects and reduce waste, leading to improved overall performance. Both TPS and just-in-time manufacturing advocate for the reduction of inventory levels to the absolute minimum required for smooth production flow. This helps to avoid overproduction, minimize carrying costs, and identify issues promptly, leading to greater efficiency. TPS promotes the use of small production batches to reduce lead times and facilitate faster changeovers between different products or variants. Producing in smaller batches enables greater flexibility and responsiveness to customer demands. The 7 forms of waste in manufacturing. Minimizing inefficiencies for sustainable growth. In the realm of manufacturing, the pursuit of efficiency is paramount. Identifying and eliminating waste is a central tenet to achieve operational excellence. The concept of waste, often associated with lean manufacturing, refers to any activity or process that consumes resources without adding value to the final product. By recognizing and addressing the 7 forms of waste, manufacturers can optimize processes, reduce costs, and enhance overall productivity. The first form of waste is overproduction, where a company produces more than demanded or before it is needed. This leads to excess inventory, storage costs, and increases the likelihood of obsolescence. Second is inventory, representing the resources tied up in materials and products that have not been processed or sold. This can lead to additional storage expenses and reduced cash flow. The third form is waiting, referring to idle time during the production process. Whether it's equipment downtime, delayed approvals, or inefficient scheduling, waiting contributes to lost productivity. The fourth is transportation waste, arising from unnecessary movements of materials or products between workstations. Minimizing these movements optimizes workflow and reduces lead times. The fifth form of waste is overprocessing, which involves adding more value to a product than is required by the customer. By understanding customer needs and streamlining processes accordingly, manufacturers can avoid unnecessary expenses. The sixth is defects, which result in rework, scrap, and customer dissatisfaction. Investing in quality control measures helps mitigate the impacts of defects on both financial and reputational aspects. The final form of waste is underutilized talent, where companies fail to harness the potential and ideas of their workforce. Employee engagement and involvement in continuous improvement initiatives can lead to innovative solutions and increased overall efficiency. Gemba is a Japanese term that means the real place or the actual place. In the context of process improvement and lean manufacturing, Gemba refers to the practice of going to the actual location where work is being performed to observe and understand the process firsthand. It involves direct observation of work in its natural environment, allowing for a better understanding of work practices, identifying inefficiencies, and finding opportunities for improvement. Gemba walks are a common practice in lean methodologies, where managers and team members visit the shop floor, production lines, or any other workspace to gain insights and make informed decisions based on real-time data and observations. By engaging in Gemba walks, organizations can foster a culture of continuous improvement and make more effective changes to enhance productivity, quality, and overall efficiency. Exponentially smooth forecasting is a popular and effective technique used in business and economics to predict future values based on past data while giving more weight to recent observations. It is particularly useful when dealing with time series data, where there is a sequence of observations over a period, and the goal is to anticipate trends or patterns for future periods. The exponentially smooth forecast is derived from a simple formula that takes into account the previous forecast and the most recent observation. The formula is as follows: Ft equals alpha times dt1 plus 1, alpha, times Ft minus 1, where Ft is the forecast for period t, dt1 is the actual demand or value observed in the previous period, t1, Ft1 is the forecast for the previous period, t1, alpha is the smoothing factor, which lies between 0 and 1. The smoothing factor, alpha, determines the weight given to the most recent observation. A smaller alpha places more emphasis on past data, while a larger alpha gives greater importance to recent data points. Choosing the appropriate alpha is critical, as it affects the responsiveness and accuracy of the forecast. Smaller alpha values result in smoother forecasts that respond more slowly to changes, while larger alpha values yield more reactive forecasts. The process of using exponentially smooth forecasting involves an initial forecast for the first period, F1, and then applying the formula iteratively to generate forecasts for subsequent periods. The forecast for each period is updated using the observed data, refining the accuracy of the prediction as more information becomes available. Exponentially smooth forecasting is particularly advantageous when dealing with volatile or fluctuating data, as it provides a balance between historical trends and recent developments. It is a valuable tool for businesses to make informed decisions regarding inventory management, production planning, budgeting, and resource allocation. Additionally, it is relatively easy to implement, requiring only basic mathematical calculations and historical data. However, It is essential to recognize that exponentially smooth forecasting is not without limitations. It assumes a certain level of stability and regularity in data patterns, which may not hold true in highly unpredictable situations or when encountering abrupt changes in demand or other factors. As such, it is crucial to supplement this technique with other forecasting methods and remain vigilant to the possibility of unexpected events that may disrupt the forecast accuracy. Let's look at a company with similar demand numbers as the example from back in Module 4. The week 1 demand is 20, the week 2 demand is 60, the week 3 demand is 30, the week 4 demand is 20 and the week 5 demand is 40. Using FT1 equal to 25 and alpha as 0.2, the exponentially smooth forecast for week 2 is 24. To calculate the exponentially smooth forecast for week 2 using the given data, the formula is as follows. FT equals alpha times DT1 plus 1, alpha, times FT1, where FT is the forecast for week T1, DT1 is the demand for week T1, FT1 is the forecast for week T1, alpha is the smoothing factor, alpha, and is given as 0.2 in this case. Now, let's calculate the exponentially smooth forecast for week 2, F2. F2 equals 0.2 times D1 plus 1 to 0.2 times F1. Or 0.2 times 20 plus 0.8 times 25. So, F2 equals 4 plus 20, or 24. So, the exponentially smooth forecast for week 2 is 24.